Hello, my name is Sarah Brown, and today I'll be presenting our work, Externalizing Mental Images by Harnessing Size-Describing Gestures, Design Applications for a Visualization System, on behalf of my co-authors, Dr. Sharon Lynn Chu and Nihal Rani. We come from the Embodied Learning and Experience Lab, or LX Lab, at the University of Florida. Our research is derived from a specific vision of how technology may support creative endeavors in the future. When we provide descriptions of objects, stories, or settings, we're trying to convey a specific image for the other person to recreate in their mind. A powerful component of natural conversation that we use to convey these mental images is the use of gesture. We envision the use of a gesture-based visualization system to harness the power of these gestures in order to produce meaningful visualizations of user mental images in support of their creative endeavors. For example, imagine a team of furniture designers gesturing among themselves to convey the idea for a new design. The gesture-based visualization system observes their gestures and produces a real-time visualization of the furniture, which helps to establish common ground between team members as they spin more ideas off of one another. It's important to note that they're not gesturing specifically to the system, but rather producing gestures subconsciously in a natural manner that arises from their brainstorming session. While in most HCI research, the aim is to use gestures as a means of interaction with different interfaces, our aim is to use gestures as a means of externalization for user mental images. So the key difference here is we intend to interpret meaning from natural gestures produced, not interpret gestures as a form of interface control. So many taxonomies are used to understand how gestures convey different kinds of information. Perhaps the most commonly cited is that of David McNeill, who differentiates between gestures that describe abstract concepts and iconic gestures, which describe concrete objects. These gestures are the closest look we get into another person's mental image of what they are describing. And when we say mental image, we refer to the image held in a person's mind which they are trying to communicate, often through the use of gestures. When it comes to producing and interpreting gestures, many factors are at play. One is the speaker's frame of reference, or how the speaker situates their description of an object from their perspective. There are three main frames of reference we refer to: the absolute, intrinsic, and relative frames of reference. When a speaker takes on an absolute frame of reference, they are situating themselves from the perspective of an absolute coordinate system. Following the example shown here, where we're aiming to describe the location of the ball, you would describe the ball as being east of the box. For the intrinsic frame of reference, the description is grounded in the intrinsic properties of a ground or a reference object. For example, using the box as a ground object, we would say the ball is by the green side of the box. For the relative frame of reference, the speaker grounds their description in their own perspective. So in this case, from the perspective of the speaker, they would say the ball is to the right of the box. Additionally, the feedback provided by a listener, be it another person or a conversational agent, can affect the kinds of feedback the user provides in return, influencing the way they communicate. This feedback loop is affected by the ability of the listener to produce subtle feedback, such as conversational gestures, engaging in mimicry, or providing emotional feedback and other nonverbal behaviors. And now I'll move on to our work. So this vision is far away from us yet. The main reason for this is that systems are not currently powerful enough to implicitly understand the information provided by people in natural conversation, such as their gestures. Thus, our goal is to chip away at this enormous problem by deriving implications for the design of such a system using a prototype system which visualizes gestures that convey the dimensions of objects. Previously, we conducted a preliminary study which investigated the physical features of iconic or image-describing gestures that people use during storytelling. Gestures which described an object's dimensions held the most consistent physical features and tended to use both hands moving in mirrored directions with typically flat hand shapes, shown in this image here. These gestures conveyed the width, height, or depth of a given object, with the length for a given dimension being conveyed as the distance between the hands. Following the results from our preliminary study, we prototyped a system that would interpret dimension-describing gestures into a visualization of an object's size. Thus, the system was designed to fit a two-dimensional image of an object between the hands. For this, we implemented the use of OpenPose, a real-time key point detection library for the body, face, hands, and feet, which identifies 21 two-dimensional key points for each hand from a continuous frame. We did not implement any gesture recognition in the system. It was unable to identify which gestures describe images or dimensions. Our focus was to understand how to design a gesture-based visualization system such that it can produce accurate visualizations of a user's envisioned object dimensions. Gesture recognition, therefore, was achieved using a Wizard of Oz method. A researcher interface was built, which allowed the researcher to capture gestures in real time that potentially bore dimension-relevant information, and then select the correct frames by hand, which would be used to produce the final visualization. As the system only produced two-dimensional images, only gestures conveying width or height were captured. From the user's standpoint, they were presented with a scenario in which they pick a gift from a virtual selection and then describe the size of the gift for a character that was shown on the right. My apologies. We investigated the use of two types of system agents in our prototype gesture-based visualization system: a live agent, which was a live video feed of the researcher, shown above, and a virtual agent, which was an automated character named Emily, shown below. This was to see if the kind of listener present in the system affected the way the user gestured to the system. Now I'll take you through a walkthrough of our system from the perspective of the user. The first step presented to the user when interacting with the system was to select a gift off a selection provided on the gift shop shelves. The gift was intended for the character on the right, which cycled through a variety of differently sized cartoon characters. The user then confirmed the correct gift was chosen. Here you can see the virtual agent Emily updating her responses as we go through the steps. In the live listener version, the researcher responded through a webcam feed on the interface. For the next 3 steps, the gift was hidden again, so the user focused more on communicating to the system listener as opposed to the gift itself. First, the user was asked to describe any customizations they would make to the gift other than its size, to enable them to focus on the size of the gift later. Then, the user was asked to stop and think carefully about the size of the gift, and to let the system listener know when they had a size in mind. This was to ensure the user had a consistent mental image in place for the following steps. The user was then asked to describe the size of the gift. At this point, the researcher began capturing gestures through OpenPose. If for any reason the user did not gesture initially when describing the gift, there was a button the researcher could press to make Emily gesture for them to visually show her how big the gift was. And in the case of the live system listener, the researcher would perform a similar gesture. Finally, the system asked the user to manually manipulate an image of the gift they chose using an Xbox controller to show their envisioned size of the gift according to their mental image. This would serve as a baseline of the user's mental image of the object's size with which to compare the system-generated visualizations. After a character was run through both the live and virtual system listener interfaces, the system produced this rating interface, which would compare the system visualizations, shown right, with the user manually sized visualizations, shown left. This was across the gift size for a given character, with the live system agent condition, shown above, and the virtual system agent condition, shown below. For each row, the user was asked to give us their perceived accuracy of the system, comparing how they manually showed their mental image to the system's visualization generated from their gestures. And now I'll discuss our study design. In our study, we asked the following research questions. The first being, does the prototype system accurately visualize a user's mental image of an object's dimensions based on 2 things, the measurements of the system-produced object visualizations, and based on the user's perceived accuracy of the system? Additionally, we asked what factors affect both the accuracy of the system's object visualizations and the user's perceived accuracy of the same visualizations. Lastly, we asked what are the possible scenarios of use for a gesture-based visualization system of this variety. The study employed a within-subject design and followed an A-B-A-B pattern, A being the live person and B the virtual agent, with regards to listener type. Thus, the participant would first interact with the live person, the first A acting as baseline, followed by the virtual agent, which would be the first B acting as the treatment condition. and then the live person again, the second A, and finally the virtual agent again, the second B. We chose this pattern because interacting with a live person is a process that everyone commonly engages in, as opposed to interacting with a virtual agent, thus it served as baseline. Each A-B pair can contain the same characters for which the user described gifts for comparison. In total, we recruited 26 participants to take part in our study through our department's SONA recruitment system. For our protocol, we went through the following steps. After informed consent and demographic information were gathered, each participant was taken through a system tutorial where they practiced using the system interface with both system agents for two gift description tasks per agent. For the main study tasks, the user went through 16 gift description tasks, which consist of 4 tasks per A or B treatment. After each A-B cycle, they rated the system visualizations for the tasks prior. At the end of the study, we conducted a perceived use interview, where we described to the participants what an ideal system would look like under our vision, one that could take in natural conversation and gestures and produce meaningful visualizations from them. Then we asked participants if they could think of any potential uses for such a system, and how often they would use it if it were applicable to them. Now I'll break down our data analysis and results by research question. This won't mention all of our results, just a selection of the more relevant ones. Our first research question looked at the accuracy of system visualizations. To answer our first question, we started by calculating measurements for the system and user-manipulated visualizations in terms of width, height, area, and ratio. We detected a systematic offset in our visualizations. These amounted to an offset of 0.396 in our width measurements and 0.372 in our height measurements. Thus, we also calculated these measurements with the offset accounted for. With the offset accounted for, our prototype system had no significant differences between the system-produced visualizations and the manually produced user visualizations. As you can imagine, the goal for the system would be to have no significant differences between the system visualization and the manually created visualization that reflected the user's mental image. We only achieved this with the inherent system offset accounted for. We also examined perceived accuracy as a facet of our first research question. Bivariate correlation tests were ran between perceived system accuracy scores and the visualization measurement differences. There were strong correlations between participant perceived accuracy scores and visualization differences for all measurements, and we found that the smaller the measurement difference, the higher the perceived accuracy score. This is to be expected, as a smaller measurement difference shows the system visualization more closely matched the user's mental image. Our second research question investigated the kinds of factors affecting actual and perceived visualization accuracy. This involved an analysis of speaker frame of reference. We examined speaker frame of reference for 25% of all tasks due to the effortful nature of gesture video analysis. Earlier, we described the 3 frames of reference in terms of describing an object's position. For identifying frames of reference for descriptions of an object's size, we used the following parameters. For an absolute frame of reference, specific dimensions had to be uttered or an exact size shown by the hands. For an intrinsic frame of reference, the speaker had to mention a ground object and gesture with respect to it. For a relative frame of reference, the gesture had to take on an internal viewpoint, such as by performing an action or gesturing to oneself. Our statistical analysis showed no significant difference between system listener types in terms of visualization measurement differences, though the A-B-A-B trends, where A was the live listener and B was the virtual agent, showed larger differences in the virtual agent in terms of visualization ratio. There was also no significant difference in the visualization measurement differences in terms of frame of reference, though there was a marginally significant difference in terms of area between absolute and intrinsic frames of reference, with intrinsic possessing larger area differences than the absolute frame of reference. Interview responses were analyzed for 2 overarching themes: system use, as in the proposed application area for the system, and system purpose, as in the role the system played in the proposed use. This consisted of translating ideas into visualizations, searching for existing things, such as various products, or customizing existing things. We found that perceived uses varied, but most participants saw the system as being used to translate ideas, which closely aligns with our vision for a gesture-based visualization system. And I'll wrap up with a discussion of our research questions. So our first research question asked if the prototype system accurately visualized a user's mental image of an object's dimension based on the measurements of the system-produced object visualization and based on the user's perceived accuracy of the system. We found that the system did accurately produce visualizations close to the measurements of the user's mental image, but only with the inherent system offset accounted for. We also found that in general, the users thought the system had average accuracy, though this could change in the future with the inherent offset accounted for before system use. We also asked what factors affect the accuracy of the system's object visualizations and the user's perceived accuracy of the system's object visualizations. We observed a marginal effect where with a virtual agent as opposed to a live listener, users produced larger differences in system visualization ratios, potentially due to lesser feedback from the virtual agent. We also observed that the intrinsic frame of reference led to larger measurement differences than the absolute frame. This suggests that future systems should detect frame of reference, identify the use of a ground object to situate descriptions as is used in the intrinsic frame. Unsurprisingly, the actual visualization measurement differences had the greatest effect on the user's perceived accuracy of the system. Lastly, we asked, what are the possible scenarios of use for a gesture-based visualization system? And we found that while application areas varied greatly, the system purposes participants proposed tended to align with our vision of using a gesture visualization system to externalize mental images. In conclusion, many aspects of communication need to be considered in designing gesture-based visualization systems, such as the qualities of the listener and speaker frame of reference. For more insights, please check out our paper. One of the insights we left out that you may find interesting are our findings from an analysis of think aloud comments users gave that gave us an idea of what influences their perceived accuracy the most. Thank you so much for listening.